Now, in calculus, of course, calculus is a study of the process of change. And change happens when there's a process, and process happens when something continues in time. Which means we have to have a description of a continuous process, and you know that description of continuous process has a name, which has a term. It's called a function. So analyzing a function in a more rigorous way is what we call calculus. That would be like the next step in your mathematical career. And the analysis of a function comes in two flavors when you do calculus. It comes in the flavor of analyzing the change, the analysis of change, of rate of change, to be more precise, the analysis of rate of change, of how fast it changes, analysis of the rate of change, and the analysis of the area under the graph. Of the area under the graph. Now, when we say under the graph, we mean between the graph and the axis, the horizontal axis, the x-axis, the axis of inputs, the independent variable axis, the dimension of inputs. So this is basically two things that happen in calculus. Now, they have their technical names. The analysis of the rate of change is technically called differentiation. Differentiation, the process of differentiation, is the analysis of the rate of change of any given function, of any given picture of a function, or a function without even a picture. The analysis of the area under the picture of such a function is called integration. And those two processes actually are connected. They connect to each other through what we call a fundamental theorem of calculus, which tells you that if you do these two guys one after another, you go back to the origin. They cancel each other out. They're like inverse functions of each other. So, now, but in order to be able to do any one of these processes, any one of these kinds of analysis, you have to understand the idea of the limit. So basically, calculus is the regular algebra plus the idea of limit. Without the idea of the limit, there is no way you can know for sure how your process is changing at any given moment. So the idea of the limit is a representation of the instantaneous rate of change. You can't find what happens at any given moment unless you have an idea of the limit. Regular algebra didn't care about instantaneous rate of change of any graph. It only cared about the average rate of change, which was change over some interval, over some period, delta t, let's say. Now, instance is, of course, at a given moment, and that's way more problematic than talking about a difference in time, some range, some period. Because when we talk about period, we know the beginning, we know the end, and we can definitely find out, right, the rate. Now, the rate of change, right, the idea of the differentiation is what? Differentiation, like if you translate it, it means finding basically the ratio between two differences. That's the process of differentiation. So, now, usually, when you deal with a graphical representation of some process, let's say a typical process of distance changing in time, or being covered in time, which is a graph of distance over time, which means you can talk about velocity just by analyzing that graph. If you analyze that graph in terms of its slope and say, well, from here to here, let's say, past delta t amount of time, some couple of seconds maybe, and then the distance I traveled from home, let's say that was 0, let's say it was in meters and I was in seconds. You say, well, I traveled first with 10 meters, and then that was 15 meters away, right? All of that. And then you're like, well, wait a second, I traveled from here to here, let's say point P and point Q, right? Basically, the two questions that can be asked in math are this. First question would be the regular question, would be, what was the average rate of change of your distance in time? Right? On average, between, let's call this T1 and T2, and let's say between T1 and T2, what was your average rate of change of distance, of your distance? Well, the average rate with which your distance was changing, according to the picture, was, well, it changed from 10 to 15, so 15 minus 10, that was the extra 5 meters, during, however much this time was. Let's say this was, I don't know, maybe 5 seconds, and that was, let's say, 8 seconds. Well, between 8 and 5, right? In 3 seconds, you moved 5 meters, whatever the direction was. Could have been north, west, south, doesn't matter, in one particular direction. Well, 5 over 3 now is a number that describes a certain quality not only of your process, but also of the picture. So if you talk about the process, if you concentrate on the process, you'll say, well, 5 over 3, 5/3, is the rate of change with which my displacement or distance was changing in time while I was walking, which in other words, physically speaking, means speed. So that was my speed. That wasn't just my average rate of change of displacement, but in other words, it means velocity or speed. Well, velocity is the idea that incorporates direction, so it will have to use the idea of displacement instead of distance, but it's okay, in this case, it's the same direction, so we don't care, it's the same thing. Okay, so now this is the velocity. This is the rate of change between the two states in time. Now, but that's the physical idea, physical interpretation of that reality. What is the purely geometric interpretation? The purely geometric interpretation is rise over run. What you've done, you've just taken rise calculated the right between two states, and you calculated the wrong between same two states, and you took the ratio between the two, and you got an answer which represented the idea of velocity, because velocity is displacement over time, or speed is distance over time. Of course, you took distance, you divided by time. You should be getting anything you get should be velocity, right? But geometrically speaking, it simply meant rise over run, which means a slope. So a slope of a graph takes the meaning of velocity when your vertical dimension is displacement and your horizontal dimension is time. Which that means that there's a connection between the idea of a slope and physics behind the picture. These dimensions could have been different dimensions. It could have meant different things. It could have been physics, it could have been economics, it could have been anything, right? The two processes when one variable depends. Price and demand, supply, elasticity, any change, right? For as long as there is, exactly. So in general, calculus is the study of change. So if you have a process, it means that you have at least two variables that depend, that have an interdependence relationship, right? Of course, one of them will be dependent on the other, right? So the one that is dependent on the other is described or depicted vertically. The horizontal dimension we always use for the thing that causes change, which is an independent variable. It's not dependent on the consequence, it only depends on you. You choose, so it's independent, right? Your independence. Now, the dependence is upon the choice, and that's the outcome upon the input. But the connection between the outcome and the input is described through a function. Now, but I haven't even described the function here, right? I actually just drew a graph. So I didn't have any formal description of what I'm talking about, right? I just drew a geometric picture, just a graph, which means that we can analyze things graphically without even understanding what's behind it. And even if I didn't tell you that this was distance and this was time, I could have still asked you the same question, but in a different way. I could have asked you, what's the average rate of change of this graph between 5 and 8, right? Whatever they are. So that'll be still the same answer, right? It won't have any meaning except for purely geometric meaning, which is the meaning of a slope. A slope is defined to be the rise over run, right? This graph is not a line. It's a curve that is changing its direction all the time, which means we have to be careful with the question we're asking. We're asking about a slope, but we have to be careful. Slope of what? I've taken a difference between the y, so I basically taken delta y, and I've taken the corresponding delta x, which meant the difference between the final and the initial state, and I took them together, and I got some number. Now, obviously, I had some delta x, or delta t, whatever, but that was an interval. So, I'm not talking about an instance. Interval is not an instance. I'm talking about something that's spread throughout time, which means I can't really be talking about exact slope at any given moment. I'm not talking about a slope here. I'm not talking about a slope here. I'm not even talking about a slope here. I'm talking about the average slopeness of this graph, right? Which means that I'm approximating, right? I'm not talking about anything specific. Maybe this slope never even happened, right? Like, I don't know, like we get the 5 over 3, right, in this case. Now, 5 over 3 is almost 2, right? Now, 2 is, it's close to this direction, perhaps, right? It's definitely not the direction that the graph was taken here, and it's definitely not the direction the graph was taken here, right? It's like here, at the end, it's almost, so there's a possibility that our average rate of change that we are going to use to describe a certain period of behavior might not even be part of that behavior. It might be just an estimation. It might never even exist. Now, but if you really want to talk about what existed in time and in space, we have a name for it, right? The technical name for that is an event. There's another name, an instance. Right? So from this comes the instantaneous adjective. Now, if you want to talk about one particular event, one particular state, we can even say, a state, an event, an instance, an instantaneous rate of change, description of what happened at that instance, we have to go a little bit deeper than just this rise over run, right? Because run requires an interval. And instance says that you don't care. I don't care about interval, give me one. Well, how do you reconciliate an idea of an instance with the idea of a run? If you're going to find a slope at that moment, right? It seems like you have to have an idea of a run be present. Without a run, you can't get the slope. So what we do, at this point, we invent the idea of limit. So you add the idea of the limit at this very moment, and you say that, yes, take your rise and take your run, which means take whatever 2 points you would like to consider around your specific spot. So let's say we are interested in the instantaneous rate of change at, let's say the point S, that is between in the middle, that point S, at S, which means that I still have to take a run, I still have to do some approximation, but I can't stop at that approximation. I need to find an exact rise of run. So what I do, I apply the limit to this particular rise of a run, and I tell everybody that the run that I'm considering is only for the purpose of mathematics. I only do it because I have to find the rise of a run. I have to find the ratio. But I need to tell everybody that this run is going to be approaching a value of 0, becoming infinitesimally small, becoming basically nothing. I'm telling everybody that I'm trying to get my period become an instance. So in other words, this means that an interval becomes an instant. If I can make somehow my interval become an instant, then I get myself from the average rate of change to the instantaneous rate of change. And the only way to do it is to make sure that the bottom somehow approaches 0. This means approaching 0. This doesn't mean becoming 0. That's the fundamental difference of the idea of limit, that you can allow yourself to approach 0 in your denominator, but you can never allow yourself to have 0 be attained in the denominator. Yeah, because it would be nonsense, right? But there's a good news, which is if top is also 0, then actually you are saved. That means f depends on the x. That means f depends on the x. That's what it means, right? That's all it means, right? The first guy is the guy who is depending on the thing that's inside. It's like a stomach. The stomach functions just because of food inside. Whatever the food is there, your health is basically the function of the food in your stomach, right? Or something like that. Or the process of F depends on what happens to X. Yes. The only thing that we put into the bracket here is the letter or the symbol that designates the variable that is independent. If you want to put square here, that would be weird, right? Because then it will mean that my inputs are all squares of somebody, right? There's a way, of course, there's a way of saying it, but we don't see it in normal math, right? It might be in some higher math. I guess you might have asked something else if the description was, and then the description follows. What's the description, right? What is the process? What kind of a process, right? How does F depend on X? And that's a description. Or in other words, it's actually a prescription of what will happen to X. It comes into existence, right? Like let's say like that. Let's say you have X squared, gets squared right away after you plug it in, and then has an experience of 16 being subtracted from it, and then after all of that has an experience of being divided by, let's say another thing, let's say X, he happens again in the bottom, but then he happens there with the addition of 4 being experienced. Okay, so altogether, that is now a description of what's happening, or a prescription of what you have to do in order to create a function. Now this is a weird function in which the question of domain actually becomes legit. Like, it's a good question to ask. What's the domain of this function? What is the range of all allowed X values? And this is the most important word, allowed. Now, is there any value? Is it all real numbers? And again, we just restrict our attention to real numbers here, right? Of course, we could have been using complex numbers as well. The complex numbers are those guys who can be negative even if you raise it to an even power, right? Just whatever we just call it. We have to invent them in order to solve certain problems. But that's usually high level, like quantum mechanics problems. Either this guy allows you to use anything you want, any real number, or there is a restriction. And if there is a restriction, we would put it like that, like a slash. Slash means unless, right, or without. Let's say without. So except for is a better word. Except for. Now, is there any value of any real number that you're not allowed to use in this expression? There is actually, right? -4. Now you see. So x equals to -4 is not allowed. So, and that's the only restriction. Everything else is allowed. You can use any other number. Anything to the left of -4, anything to the right of -4. Rational numbers, irrational numbers, whatever. But isn't this x squared minus 16 a difference of squares? Because 16 is just 4 squared. And if that's the case, isn't that just x minus 4 times x plus 4? Because any difference of squares is that in other way, right? That's another way of saying it. And if that's the case, then why wouldn't I be able to cancel the x plus 4 at the bottom with the x plus 4 that I just revealed in the top? That's perfectly allowed. You get x negative, but you still have to communicate the fact that before I did any algebraic manipulation, the state of reality was such that -4 wasn't really allowed. Yeah, but I can do a manipulation, and I can arrive at a conclusion that disregards the existence of x plus 4 in the denominator somehow. And do you know what that is about? What's the meaning of this disregard? This is basically the idea of the limit. This is the idea of the limit. But now let's come back to the limit. If somebody asks you, what's the limit of this function, Xavier, of f of x as x approaches, I'm not telling you to use it, I'm telling you to approach it. Now you can approach it graphically, or you can approach it in your own abstract mind. What does the function itself approach when x approaches -4, right? That would be the English language transcription of this statement, which is, what value does f of x approach? So basically the whole function. The y, the vertical, the height, whatever, approach while simultaneously, right? It's a continuous process. You track. You go on the x and you track what happens to your answer. Approach while x, and I'm going to use an arrow. Arrow represents approach, the word approach. Approach is -4. And in fact, I am not even saying from one direction. I'm not saying from the left of -4 or from the right. I'm saying from both directions. That's what we call a total limit, like a total capturing of the situation. Yeah, it's a capturing of situation, even if you can't grasp it. And by grasp it, I mean not grasp it in the mind, I mean grab it with your hand. There are certain situations that you cannot really touch. You can't take it. But you can still understand where that situation will take place. Like you can understand where it will take place without being able to attain it. And this is one of those situations.